Hello and welcome to another episode of Vibrance Learning Lab. Today we have a webinar, cell phone videos pulled from, we have boat shapes pulled from cell phone videos to help you with your machine monitoring. My name is Brian Richardson. I'm Director of Sales here at Vibrant. Dr. Mark Richardson. And we got about an hour presentation to go through today. And if you have any questions, go ahead and drop them in the question box. We'll get those wrapped up at the end of the presentation today. And I guess I'll leave it to you, Dr. Mark, to take it from there, and I'll catch on at the end.
Okay, thanks, Brian. We've got a lot of material here, and I'm going to go through it rather quickly. And I want to start off by showing you or taking you, this is our website, the Vibrant website, vibetech.com, and I'm going to go under resources down here and to technical papers. This is a paper that I'm going to present at the Vibration Institute, ATC, I forget what all that is, but it's the VIA ATC 2025 in Norfolk, Virginia next week. So we're going to be there, and Vibrant's going to have a table and a booth and showing off MEscope. But let me just take you through quickly this tech paper. And you can see if you click here, you're going to get download a copy of the PowerPoint presentation that I'm going to go through in more detail here in a minute. So all this material we're going to cover today. If you're busy, we get started. Maybe you don't have an hour right now. And of course, the whole session will be recorded and available on the Vibrant website, the YouTube website. So anyway, this is son Shawn and I that have been working together with something called FACS. And we're going to get into that because that stands for Fault Correlation Tools. And you can think of MEscope as just the whole series of tools that you have in your toolbox to process data and analyze vibration problems, resonant problems, whether it's, you know, you're just testing an airplane wing with a shaker, or something small with an impact hammer, or in the case of a rotating machine like this, just the machine running by itself is creating vibration. So we're going to get into all the different details of collecting data with your cell phone, processing that data, curve fitting what we call ODS-FRFs. That's a special measurement that we make. And then we're going to use FACS, which is a form of artificial intelligence or machine learning. These are the new buzzwords out there all over the planet now. And everyone is using machine learning or AI to associate a set of data with a particular, in this case, a fault or identification of a machine condition based on its vibration. So that's what it's all about. This is a right up here of a neural network, which is the computer model that's used to model your brain. And neural networks are trained with lots of data. It's just exactly like a child learning how to ride a bike. You need lots of trials before, you know, all of us figured out how to balance and use the handlebars to steer a bike. So that's a good example of how neural networks are a good model of our brain. So this kind of shows the two pieces. You label the data. I drive a Tesla, so for instance, there's lots and lots of videos collected with pictures of stop signs and stop signs can have graffiti all over them and so forth. So the neural network has to be trained with lots of video data to identify a stop sign. And then in my car, there's an algorithm slightly different called an inference engine, but it's a trained neural network and it drives the car for me. It's just an amazing software. So FACS behaves very similar to that, only it uses shape data. And we're going to look at using mode shape data that we extract by curve fitting a set of ODS-FRFs that we've taken off of a video, a cell phone video, or a number of cell phone videos. So here's kind of a block diagram, same sort of a thing. We label the mode shapes with an unbalanced, or just came out of maintenance, or this is a smooth running machine. However we want to describe or label a set of mode shapes. We feed those into what we call an archival database. And this is one of the options to MEscope, where you can put an archival database into the cloud. We give you all the software to do that, or on your company network. I'm going to run the software later on here from a version of it that I've just initiated on my own computer. So then if we take current mode shapes, let's say we're out taking data in the field or factory, and we feed that into the archival database, FACS is a search algorithm that will compare those mode shapes with all the labeled mode shapes in the database and identify the closest match between the mode shapes of the current data versus what's already been labeled and archived. So functionally, it's similar. The one advantage is that FACS will work immediately with any data that you archive in the database. It doesn't require a lot of data like a neural network in order to function properly. But we've trained a neural network here at Vibrant. We did it years ago with mode shape data, and then we feed it some data with a little bit of noise on it, and it says, well, that's only 90% like the data that I'm used to seeing. So a neural network will give you the same result as FACS, but FACS will work right out of the starting blocks with any data that you put into the database. We're going to talk about TWFs, time waveforms, DFTs, discrete or digital Fourier transforms. Those are what are called a transform pair. And what MEscope does is it takes videos, and we're going to go through the details, and then it animates the data. So you can animate the ODS data by sweeping a cursor through the time records, or using sinusoidal modulation in the DFTs, or the frequency records. So we can look at the ODS, operating deflection shape, as a function of time or frequency. And so we'll get into that. And then we use a point grid. And so this is all showing that, and we'll come back to all that. So I just want to hit some of the highlights here. And then scaling. The algorithm we use to extract the time waveforms from the video measures displacement from frame to frame to frame. So it looks at the difference between a pixel location in one frame versus the next versus the next. But we'd like to scale this data, time waveform, just like we do with accelerometer data. With accelerometers, we scale from voltage to G's of acceleration. With videos, we can scale from displacement to inches of displacement, or millimeters or centimeters of displacement. So we'll go through some of that. The advantage of an ODS-FRF as opposed to an FRF, a frequency response function, is that we can't measure the force. So when we can't measure forces and then calculate FRFs as the response divided by the force, we calculate ODS-FRFs. So we'll get into some of that and how we do all that. And the advantage of it is that it has the same units as the TWFs. So if I have ODS-FRFs in inches, I can differentiate to inches per second, which many machinery people they want to look at data in velocity units, because the rule of thumb is if a machine is vibrating over an inch per second, it's about ready to break loose and go through the ceiling. That's a lot of vibration. Law of the FFT, we'll talk about this too, and that is that the frequency resolution, delta F, between samples of the DFT is 1 over the time length of the recorded time record, the TWF. So they're linked together. Now, here's something that's a unique feature of videos versus an analyzer. Analyzers that measure accelerometers or velocity or displacement, however the data comes in as a voltage, they have what's called an anti-aliasing filter, which filters out all the high frequencies. That's not true with a video, but what we have are aliased. If we have an order, this is a picture here of the first order, the running speed of a machine at, let's say, 1,000 RPM. And here's the second order, 2 times that speed. Well, it's not at 2,000 RPM. It's aliased about what's called Fmax, the max frequency of the data. So we'll get into some of that and talk about how we can actually identify those. Another advantage of ODS-FRFs is we can do spectrum averaging. A DFT is just the Fourier transform of a time waveform, TWF. But we want to do spectrum averaging that gets noise out of the data, that gets rid of distortion. But if we're going to curve fit ODS-FRF data, we've got to do some special things. Experimental mode shapes is called EMA, and EMA is an experimental modal analysis. So we use that term, and when we talk about EMA mode shapes, those are what we extract from either FRF data or ODS-FRF data. So this is just a mode defines a resonance, it has a natural frequency, it has a Q of the resonance, and the standing wave motion is what we call the shape. Here's some other rules that are just good to keep in mind. Universal laws of modal analysis. Any object with mass and elasticity will vibrate. So that's all that's needed to create resonances. However, some forces have to be applied in order to make it vibrate. Resonant vibration is defined by mode shapes, very fundamental. Virtually everything on Earth will resonate under the right conditions. All modes are excited at all frequencies. That is an assumption we use in curve fitting. So we'll get into some of that. And then all vibration is a summation of mode shapes. So we're going to talk about an ODS versus a mode shape. We'll come back to some of this. And then the topic of this webinar is using mode shapes for machine monitoring. So we'll get into curve fitting. Here's an example of curve fitting, and then an animated display of the mode shapes, and then facts. And this is showing how we're going to use facts, the facts bar chart, which is mainly what facts is. It's a search algorithm. It searches the database, puts up a bar chart using a correlation coefficient, which is an MEscope called SDI, or shape difference indicator. And then we got results for different unbalanced conditions. So let's put this down. Oh, I want to say one more thing. If you don't own, well, you either own MEscope or you don't own MEscope. Either way, if you purchase our modal analysis package and our video processing option to that package, we are offering a free seat in a hands-on modal testing and analysis course, which is held here by another company called Navcon Engineering Network here in Southern California. I am talking to you from Southern California. the Vibrant office is still in Denver, but we're using the internet, and this is not a Zoom meeting. We're using a different set of software, but the same idea. But if you purchase the technology we're talking about today, we'll give you a free seat, and you can see each seat is $34.50. And if you want to send 2 or more people, then of course you have to pay for them. And the next course is coming up in August. There might be room in that course. I'm not sure. You'll have to contact NavCon, and then of course there's another one in November. So these are all things to keep in mind as we go through this software today, and we're just going to use MEscope to cover, you know, this whole broad range of topics here that that I'm talking about, that I've already introduced. So let me go and bring up some PowerPoint slides, and I'm going to put them into the display mode here. And well, we're all at the end. Let's go all the way back to the beginning. I was kind of reviewing them here this morning before the meeting. So we're going to start out here, and this again is my presentation for next week in Newport News, Virginia, and a few introductory slides on using your cell phone. And of course, this is an iPhone here, and there's different settings. There's you can record videos with different you can see what's called HD or high definition, 30 or 60 frames per second. And I lost my mouse here. I don't like that. Let me see if I can get it back. I'm just going to, yeah, so I have a mouse, and if I just look at each slide individually, so we're going to stay, I don't know how to get the mouse up, but I like pointing to things as I'm talking about them. We're going to look at some video data that I recorded at 120 frames per second. And that's called the slow mode operation of the iPhone. So here's, you know, just a comparison of the bandwidth, of course, is, or the sampling rate is less than a camera that you can purchase, which will go up into the kilohertz. Vibrant Resell is one that can measure up into the kilohertz region, but your cell phone is in your pocket. Why not use it if you can, in fact, extract mode shapes from videos that were recorded at these lower speeds. HD versus 4K, we're going to look at data that was actually recorded at 60 frames per second, which is 3,600 RPM, or half of that is 1,800 RPM, Fmax. Now, Fmax is the maximum frequency in the DFTs or in any of the spectral data that we may compute from the time waveforms. But you can see that there's just a lot of pixels. There's a lot of resolution, and they're almost simultaneously sampled. That's another issue. If you spend a lot of money for a fancy camera, the electronics may be simultaneous. The phase difference between the top and the bottom of the video is so small that you can just assume that it's simultaneously acquired. So you don't need to spend a lot of money for a fancy camera. And 8 million pixels per frame. That's almost like having 8 million accelerometers measuring two-dimensional motion in the frame of the video. So a lot of resolution. Here's something else to keep in mind. I already mentioned this. Delta F is equal to 1 over time. So if you want good frequency resolution, you have to take more data. If you only take 10 seconds of data, you get 1/10 of a hertz resolution, or 6 RPM between samples of your spectrum data. So we're going to curve fit the spectrum data and get mode chase from it. The examples I'm going to show later on, I took 30 seconds of data. Then I threw away some of the beginning and ending of the samples, and we'll talk about that. You should get the machine into the field of view as large as possible and use a tripod for stability. If you're taking data on a ship, we have background removal algorithm in the software so you can take out some more of that vibration. What you want is the vibration of the test article. Here's an example. Let me just see if this is, oh yeah, down here. In your phone, this is taking out all the slow-mo frames because you just want the 120 hertz. Before you copy this video, these frames, either using your Google app, you can copy in the cloud, or you can save these to the iCloud, the Apple iCloud, and get them into your computer. So you can go out in the field, the factory, anywhere, take a video with your cell phone, wirelessly move the video over to your iPad or your portable computer, and use MEscope to process the data. So let's move a little faster here. These are some issues with spectrum averaging, which we're going to use to compute the ODS-FRFs. And we use what's called overlap processing. This is another feature in MEscope where even if I only have 30 seconds of data, now if you're using an FFT analyzer, you can take, minutes worth of data and do averaging with a smaller subset of that time waveform data. With videos, 30 seconds is a lot of data, and we do what's called overlap processing. So we use some of the previous frame of time waveform data and then some new samples of the time waveform, and that allows us to create ODS-FRFs with a lot of averages. So why spectrum averaging? It reduces noise and distortion. Modes are defined for a linear system. We won't get into that. You really need to take the training course at NavCon to understand all the ins and outs of spectrum averaging. A Hanning window is a special window we should apply to this type of data to reduce what's called leakage, and it's necessary for modal curve fitting. So we'll get into some of that. Advantages of the ODS-FRF, I already mentioned this, same units. So if I have TWFs in units of velocity, I get ODS-FRFs in units of velocity. If I have some accelerometer data in ODS-FRF format, I can integrate that data and compare apples and apples. Then I'm comparing the accelerometer with the video. So, for the naysayers in the world, gee, is this accurate stuff? Well, compare it with some accelerometer data, and now you have some answers to compare. We use a point grid in MEscope, unlike maybe our competitors, and we reduce 8 million pixels per frame to several thousand points in the point grid. And then we just keep the time waveforms and the DFTs for those visible points. And again, we don't care about the background, the motion of, the pixel motion of the wall behind the machine or the floor or, parts of the machine that aren't interesting to us. With these little rotor kits, what we're really interested in is to compare answers, perhaps, are a few points on the base plate and then maybe a couple of points on the top of the bearing blocks. If you're doing walk around data collection in a plant, that's typically the data you will take with accelerometers. Here is let me just start this. This is an animated picture of what you get in MEscope, so you can see your data, and the advantages of, you know, being able to see, and then you can crank the amplitude. So the machine is moving around a lot. We'll see here in a minute that the raw video doesn't show you anything. Here's a comparison of ODS versus a mode shape. People get confused. The two are related, but they're different. ODS is force vibration. Mode shape is deflection of a structural resonance. ODS can, we just saw in that previous video, any frequency, any time value. When I have 2 or more measurements, 2 or more degrees of freedom, and from a video, I have vertical and horizontal of every point in the point grid. A mode shape defines a resonance, so it has a specific natural frequency associated with each mode shape. There's no units. There's no unique values. It's called an eigenvector. Mathematically, we won't get into all that. But what's unique about it is its shape, not the values. ODS has engineering units. We're taking it right off of the TWFs or the DFTs, and they both have units of velocity, displacement, acceleration. So ODS actual is the actual motion of the machine, and that's why we want to put the magnitude and phase up on the animated picture so we can actually see in engineering units how much it's really moving around. Mode shapes define relative motion. ODS will change if the forces, the material properties, or boundary conditions change. Mode shapes will change only if the material properties or boundary conditions of the machine change. So material properties is probably the most interesting for machinery health monitoring. The material properties are going to change. The bearings are going to wear, the bolts are going to loosen, the couplers are going to loosen, and so, and then EMA mode shape is extracted from ODS data, and we'll curve fit that data. And so let's keep moving here. We're chewing up a lot of time. Here's a description of a EMA mode shape. Let's just go through and look at some of these. There's a lot of, let's just get them all going here. Soft foot. I mean, there you clearly from a cell phone video, you can see a problem with this machine, and there's a bunch of examples in here. And you know, vibration is too fast, displacements are too small, so it allows you to see what you can't see from the raw video, and parts that can't be instrumented. So that's certainly the case. You can't put accelerometers in various places. Here's some pipes. One is vibrating, the other one is completely still. So you can't shut down the machine. Operations people don't allow that. And during normal operation, there's no way to get vibration any other way without shutting it down and putting accelerometers on there. Here's again, using the point grid, I can pick points out. The point grid is behind the video frames. And so I can get the magnitude and phase of various points on the machine to see how much is it really moving. So here's a point that's moving at 1/2 an inch per second. That's getting up there. That's inch per second is a danger zone. It's a complex shape, so we have to have animation that shows not only the magnitude, but the phase between different points on the test article. Here's another advantage. When you use a high-speed camera, typically you got to use floodlights. Your cell phone has some amazing technology in it that allows you to take a video like this in a dark place and begin to visualize how that machine is, in this case, just rocking back and forth on its base. Okay, well, let's just move on here a little faster. Here is the animated picture in MEscope that we get, where we have the graphics from the video along with data. You can see the cursor is moving around here. Now it's doing a sinusoidal animation from the DFTs. Here's a little review of terminology. We've already covered some of this. Time waveform is what we extract from the video, and in your cell phone, FPS, frames per second, is the recording frequency. Well, that's the same as in an analyzer, hertz, CPS, RPM. They're all related to frames per second. We're going to extract thousands as opposed to millions of time waveforms. Millions is just too much data, so in MEscope we reduce it to a point grid, which we can work a lot better with. But we can, okay, so this is, what's this about? Well, this is a time waveform. This is a sweep showing this machine just bouncing around. But all conventional signal processing methods can be used on these time waveforms. So they're identical to the data we get from accelerometers using an analyzer or a digital data acquisition system. We use Hanning windowing, just like we do in the analyzer, to minimize leakage around the leakage is, the spectrum is leaking out of the resonance peak into the surrounding channels of data or samples of data. And we also remove noise from the data. So curve fitting works a lot better. Okay, we've already been through the little bit of the neural network training of your brain, and let's just skip over this and go a little faster because I want to get down to FACS. And so here's what FACS does in terms of doing a database search in an archival database where I put mode shapes into the database. And this is all MEscope software that does this. And then when I have some more data, FACS will do a search with the new mode shape data and compare it with what's already in the database, which has been labeled with, in this case, we're going to look at unbalanced conditions. So we use something called the correlation coefficient. The more popular one is called MAC, Modal Assurance Criterion. And that's a way of comparing two mode shapes. But that only measures the collinearity between the two mode shapes in n space, if you will. You know, they can have thousands of degrees of freedom. In this case, we're only going to have 8 degrees of freedom. The motion at the top of the motor and the top of the bearing blocks. So we're going to work with a lot less data, but shape difference indicator is a little more accurate than MAC in the sense that it compares the actual numbers in the two shapes with each other. And its values are all between 0 and 1. So this is, FACS uses this so that this correlation coefficient, all the values are between 0 and 1. If the value is 1, that means they're identical shapes. Numerically, they're identical. Magnitude and phase. I can change a little bit of the phase or the magnitude, and the value of FACS will be maybe 0.9, or if it's below, then the shapes are different. So very simple method that we use to compare two mode shapes. Okay, so here's the example I want to show you. We're going to run MEscope, we're going to do some curve fitting, and then we're going to run FACS, which is actually a separate program called Console, Machinery Monitoring Console, which has the FACS graphics and a whole bunch of other graphics in it. I won't go through that today, but I'll just steer you to the operating manual. If you own MEscope, you can go to the machinery monitoring chapter and see all the features that are in the machinery monitoring option. So we're just going to try some simple cases here. We'll call it the baseline, a balanced machine. It's, you know, we didn't balance it with a laser or anything. It's just a machine with with no screws on these two rotors. Then we're going to take some of these screws over here and put them on to the two different rotors. So we'll put one on the inboard rotor, one on the outboard, one screw on each rotor, inboard and outboard, and then two screws on each rotor. So the two screws is going to create a lot of vibration. Okay, so here's a case of this is what you get in your cell phone, and you can see, if you just animate that video that you get out of your cell phone, it looks like this. So you can't really see much of anything. You can see the two rotors wobbling around a little bit, and you can kind of see the unbalanced screws. So I just know from looking at this that there's unbalanced screws when this video was taken. But I get it in MEscope, and boy, we just don't have, these are all supposed to run, but now I can increase the amplitude, I can slow it down, speed it up, and I can see either a time animation or a frequency animation. And now you can see plenty of motion, and you can actually see the mode shape of these rotors, which is, there's no other way to see that and visualize that. So it's just amazing stuff when you have a video. Okay, so we're going to take some data at 120 FPS, which is 7,000 RPM, and then the usable data is half of that, or up to 3,600 RPM. So you can't quite see the max here, but we've got data from 0 to 3,600 RPM. The first order is at 1,000 RPM. The second order of the machine will be 2,000. The third order at 3,000. And then you see some other things, some sideband resonances that are getting excited. But we're just going to focus for this presentation on the first three orders of the machine. And we're going to curve fit that data. Okay, well, first we're just going to go through what's called the wizard in MEscope. So when you order this option, the video processing option, we take it through 5 steps here. So very quickly, the first thing we want to do is crop all the pixels out of the video that we're not interested in. We don't care about the table. We don't care about the curtain or the wall behind this. We want to just crop it down to looking at the test article. Second step is to put in the frames per second of the video, and also we can use this little slide bar to remove some of the beginning frames, some of the ending frames. Well, why would we do that? Well, if we touch the cell phone with our finger to start the recording, it may shake a little bit, so we don't want that data. And then at the end, if we touch it again to stop the recording, we want to throw that data away. So you can see down here that we're still going to end up with 30 seconds of data, even though we're throwing away some data at the beginning and the end of the video. Okay, so here's the point grid. Now this is kind of the maximum that I can get in the wizard, but I can, I can cut that way down to just a few points if I'm only interested in a few points. And we'll see how that works in a minute. But I've got 14,000 points in the point grid, and because I've cropped the video, I still got 4 million pixels per frame. So I've got a lot of data, and the MEscope will take the data around each point grid, the pixel data, and assign it to each point grid. So that's part of the secret sauce in MEscope. Now here's the scaling. So the idea here is that you just pick 2 points, A and B, anywhere in the plane of the video or close to the plane. You don't want to pick a point way in the back here and then a point in the front. because that distance is not associated with the video recording. But I can pick any 2 points and virtually anything on the machine. In this case, I can put a ruler, or I could just lay a ruler in front of the machine, and I know that's 3 feet long, and then I could click on the ends of it and enter the distance. So you can see in this case it's 17 7/8 inches. That's the size of the machine. Okay, so here is what we call our magnitude filter. And what it does, now that it's extracted all the time waveforms, it puts up a histogram here. And these are just counts of displacements in the video from the smallest to the largest. And there's just 100 bins here. So we've broken down all of the TWFs that have been extracted already into 100 bins, and then I can say, well, let's take out some of the low displacements, and you can see that it removes all of the grid points of the background, including some where this is all black here. So the algorithm can't tell the difference from one frame to the next because they're all very black on that part of the machine. So unless I put some sort of a target on there, if I'm really interested in the motion right there, the video is going to not record very good motion. And again, with the base plate and then some of these shiny parts here on the base plate, so it's going to take out everything. But what I'm really interested in are just the motion at 2 points on the top of the motor and the motion at the top of the 2 bearing blocks. So that data will be preserved. And okay, so there we are. And this is another video showing that, you know, there's no motion to the background, there's no motion to some of these other points that I'm not interested in. So if I come down here and then I can crank the amplitude, and you can see, you know, very clearly the machine is bouncing around on its rubber mounts, and this is at 1,000 RPM, so that's what it was running at. So we get a lot of, I mean, this is kind of like a built-in tachometer. I know exactly where to look for peaks in the data. Okay, let's move on. We already mentioned aliasing. There's no anti-aliasing filtering in your cell phone. So higher order peaks that are multiples of the running speed, because that's where the primary excitation forces are coming into the machine, they will rotate, or they will wrap around 1800 RPM, and you can see them. Let's move on. We're just using up our time here very quickly. Here's kind of a graphic that shows that summation of resonant curves. All modes, all vibration is the summation of resonance curves. Okay, we've already looked at some of that. Here's a curve fit. So let's get into I'm gonna stop here and let's go run MEscope, and I'll just show you some things. And then I wanna get into the use of, okay, let's just make this large. And I'm going to open up. This is not the one I'm interested in. I'm going to open up a different project. And let's just open up this guy. So this is an example here with the 2 unbalanced screws on the inboard and outboard rotor. So this is going to create a lot of vibration. And we'll see here in a minute what it looks like. Okay, so here it is. I've reduced the model down even further. We can go back into the wizard and do this. So I just have 4 points. 2 different points on the motor and one here on the bearing block, and then another one. Now these points are selected during the ODS animation, so that I want to, and then I want to turn the point grid on. If I go up here and go to display, we'll just see, show the points. So there's the point grid of points. You can still, we still got thousands of points, and during animation, you can see that a lot of these points are all moving together. So I just pick one of them. So let me just start the animation here. So we're going to go up, animate, and let's just see what it looks like. Okay, we got magnitude and phase of the 4 points, 2 on the motor, 2 on the pump, and I'm animating out of the mode shape table here where I've got the first 3 orders. So these are mode shapes that we got from curve fitting the data, and you can see, you know, different phase difference. There's the second order, and everything's just kind of moving together, magnitude and phase of the second order. Let's go back to the first order. You can see that the first order, the running speed of the machine, the bearing blocks are a little bit out of phase with the motor. Now let's go down and look at the third order. Clearly out of phase. The motor and the bearing blocks, you know, the points are just moving back and forth, but they're 180 out of phase. And we can see that with the little phase diagrams here. And we can see the inches per second. So all this data has been scaled to velocity, and you can see at this frequency, now that's not the overall motion, but that's the motion at the resonance. Let me click down here on the ODS-FRFs. I'm going to change the cursor over here to a peak cursor. Let's put the cursor. Here's the running speed, and I've put a peak cursor up here so I can just animate. So very similar. There's the first order, and here's the second order, 2,000 RPM. Same thing we saw from the mode shapes, and in fact, the values are very similar of the mode shapes versus this is the ODS. This is just the animation of those 4 points. And again, we're seeing the out of phase motion of the third order. And if I go back here to the first order, pretty much in phase, a little bit of difference in the, you know, typically if you're looking for problems in a machine, you're gonna look at these first 3 orders, maybe the first 5 orders. And, you know, there's a lot of literature, a lot of knowledge of people in the machinery business who can say, well, that particular problem is unbalanced, or it's a soft foot, or it's a coupling problem, or a gear problem, various mechanical issues that will affect the vibration. Let's just go in here and do a real quick curve fit, and then we'll move on to facts. We haven't even gotten to facts. Well, you can see there's a curve fit here. The red curve fit line is laying on top of the data. Let me turn off the cursor. And so this is curve fitting. Let's clear this out and we'll do a quick curve fit here. I'm going to delete all the data. Yes. Now there's 3 steps to curve fitting. What's called a mode indicator, frequency and damping, and then a third step, which is the residue or the mode shape. So most curve fitters work this way. MEscope has 4 different curve fitters in it. We're just going to use one called the quick fit. And the quick fit uses the mode indicator, which will count the peaks, and we'll see that down here. Now you can see that there's a whole bunch of stuff right here, which I don't even see in this graphic up here, but I just want to get the 1, 2, 3 modes. So let me change this over to, I'm going to change this over to linear. So the peaks are a little clearer. drag, and I'll drag this threshold down. And so we got 3 peaks. There's 3 modes. Now I'll go to the next step. Well, rather than take it through the steps, we have something called Quick Fit, and it just goes through and does everything, all the steps. So bingo, you can see the red line up there. If I scroll through the data, you can see some of these FRS, the ODS-FRS don't have a peak in them, but some of them do. Those are different points and directions on the machine. And this is all this stuff here. I'm not sure what that is, but anyway, there's a curve fit. And then we save those away into a shape table. Right here, I can save them. But let's just go ahead, and I'm going to open a different project here that's already got the shape tables of all of the 5 unbalanced cases. So mode shapes, 120 Hertz. This is the one that has all the results in it from curve fitting the ODS-FRFs of the 5 unbalanced cases. Now this is a little more advanced uses of MEscope. We're using scripts, and each script has a hotkey. So you can see these hotkeys: baseline, which is no screws, 1 inner screw, 1 outer screw, 1 screw on both rotors, and then 2 screws on both rotors. So those are the 5 cases. I'm going to attach this project to the archival database. So this is all part of a different option, and now it's connected to the archival database. And I see some things here. It shows me what is actually going to archive into the database, various things that I can put in there. So let me close those, and let's bring up console, which is a separate program. Let me just bring that up and show you what that looks like. So console has a lot of different stuff in it. Now it's already connected to the database, but I can go back to home here, and so it's showing me, what is it showing me? ODS, oh, here's the gallery. So this is my project here. So I want to click on this one and open up this guy. And let me just close down some of this stuff. Here's a trend plot. So I'm now connected to the database that MEscope is connected to. And the other interesting thing is, here's the same hotkeys. So MEscope talks to this console software, and it passes the hotkeys over, so I can remotely control MEscope from console. And so let me just see if I can get this over here. Okay, so there we go. We got console, and there's a trend plot. I want to go up here, and I want to go to home, and I want to go facts. So here's my facts chart, and let's just look at facts. So you can see I'm just using the first 2 mode shapes out of the mode shape table over here, and I'm doing a comparison with facts in the database, and it's saying that the data that I sent over here is 1 inner screw, the mode shape data for that. But let me just go up here and start over and just say, give me some baseline data. So you can see it change that over, and here it is. Now it said that's the baseline mode shape data that just came in. And these are the facts values of the other mode shapes that are already archived in the database. But both mode shapes recognize what I just archived in as baseline motor. So you can see this is a tool. I can go, let me try 1 screw of both. Bingo, there it is, it recognized it. So I can just go through these different mode shapes. Over here, MEscope is archiving the data. So I could have curve fitting, I could have ODS-FRF calculations and everything set up in MEscope and run a script. Scripting is part of MEscope. We'll certainly help you with that and get it all set up for you because it's programming, and I know that most engineers don't like programming. But so this is what I wanted to show you today, and show you that the mode shapes of this rotating machine are very unique in the sense that FACS will identify whatever labeled set of data that I put in the database, and it's quite different just using 2 of the mode shapes instead of all 3. I could have FACS check all 3 of them and put that up there, but this is just a little simpler and easier. Or I could just use the first order, the running speed at 1,000 RPM. Okay, well, that's pretty much all I wanted to show you. Brian, do we have any questions?
No, we had a couple that I took care of privately, which were pretty straightforward. So no, not any additional questions at this time. If any of you are, as we mentioned, we'll be at the Vibration Institute in Newport News next week. Both of us will be there, so come stop by our booth if you're out there. Say hello to us, and we can show you some more MEscope if you'd like. We'll have it live and running. We can go through this. We're going to do this presentation again, as was mentioned earlier, in one of the breakout sessions. This recording, this webinar will be recorded. It has been recorded, so it will be up on our, if you had to jump off or you jumped off and came back on, missed some things, we will have it up on our YouTube page. You also very well may get an email from us. That'll happen next week with the recording on it. We usually do one of these about every month, so look for an email from us. We'll have a different subject in August, and we'll keep it going from there. And that's all I had. Anything else, Dad?
Well, I think the subject next month will be repeatability. What if I just take a video with my cell phone and then the machine's still running, I take another one or a third one, and then run them through the process that we went through here today of ODS-FRF calculation, curve fitting that data, and then logging that data into a database and then using FACS to compare what should be identical results. So that'll be interesting to see because people have questions, and of course, if you've been using accelerometers throughout your career, whatever you're doing as a vibration analyst or mechanical engineer in your organization, you're a lot more comfortable with accelerometers. So we want to keep showing you how to deal with videos, how accurate they are, what you can do with them, and so forth. So that'll be our topic next month. Another topic that we actually have some of you may be familiar with IMAC, which is the International Modal Analysis Conference. Vibrant goes to that every year. It's next February, actually here in Southern California, in Palm Springs. And that's I call it the club meeting. People from all over the world come to IMAC every year and rub shoulders and talk about modal analysis. Experimental, finite element derived, maybe even closed form solutions to the differential equations. And those are 3 different ways to get mode shapes and compare answers and understand vibration. So there we're going to talk about getting 3D mode shapes off of 2 cell phone videos from 2 different angles of a test article, and combining all that data in MEscope so that you can actually see the 3D motion. The video only captures 2D motion, so if the primary deflection of the mode shape is in the direction of the recording, in other words, in and out of the field of view of the cell phone, then you need to get one from a right angle, and then comparing a like point and doing ODS-FRFs and so forth, we can actually merge all that data together and get 3D motion. So that's a coming topic also. That's
Exciting.
all for me.
All right. Guess we'll leave it there, and y'all have a great day and a great upcoming weekend.
All right.
Bye now.
Bye.